EE World, I'm Martin Rowe. We are in Brooklyn, New York at the NYU Tandon School of Engineering. This is the annual Brooklyn 6G Summit, and we're here with Sarah LaSelva from NI, part of Emerson. I've got to get used to that. And Sarah is here with a demo to talk about power consumption and power measurement. So Sarah, why don't you tell us what you've got here?
Yeah, so we feel like as we look at 6G and moving into AI, moving into greener communications, sustainability, it's really important to be able to have an understanding of how your AI is performing and being able to correlate that back to power measurements and how the power of the overall network looks. So what we did is we built up, I'm going to call it a pre-6G network. So on my table here I have 3 servers. The one on the left is acting as our G node B. The one on the right is our UE, and then in the middle I have a test orchestrator and data recorder server. So what we did is we started off by taking OpenAir interface, which is an open source software stack for 5G, to get our network running. On the base station side, we pulled out some functionality and replaced it with a neural receiver. Now, I have 2 different versions of my software that are running here. I have the neural receiver, which is running on a GPU to do the processing of my machine learning model. And then I have just traditional 5G, and I can toggle back and forth between them. And then my USRPs are acting as the RF front end. And then in between, after the base station, I have a power amp that is connected up. And we were working with a university that was doing some research on fast on-off switching for a power amp. So this came out of a collaboration with them. And what we wanted to do is say, how does changing things in the physical layer, changing things in the Mac, using my machine learning model versus traditional, affect the overall power? So what we've done is integrated timing and synchronization and data labeling within OpenAir interface. So every packet that's sent is time-stamped. Then, since we're NI and we're experts in timing and synchronization and in test and measurement, we took our compact RIO system, or RIO stands for Reconfigurable I/O, where we have a selection of different current modules and voltage modules. And so we were able to integrate those into the system. And so I'm taking...
That's these modules here.
That's this guy right here. So I'm actually taking power measurements at multiple different points in the system. So, and you can see I have my breakout box where I have my current sensors where I'm measuring the power of my G node B server. I'm measuring the current coming out of my USRP RF front end. I'm measuring the voltage. And I have a couple more sensors connected up to my power amplifier as well. And then within my G node B, I'm also looking at the CPU power and the GPU power. So I'm taking all of these power measurements, I'm running all of this in a real-time network, and then what the secret sauce of everything coming together is I'm then correlating those power measurements back into my wireless measurements. So now at a packet-to-packet level, I have information about my wireless KPIs as well as my power measurements. So now I can understand as I'm turning my power amp on and off, and I can see, at a packet level when I have it on, off versus just off. I can see what's going on in the the PA per slot. I can also see my average PA. And then I can also take a look at my receiver itself where I can see the total amount of power that's used, my CPU power usage, and then I'm toggling back and forth between using that traditional method versus using my neural receiver and GPU. So you can see I just turned it back on and my GPU went up to around 50 watts. So overall, we feel like it's a pretty nice test bed to enable you to do your research, whether it's looking at AI or looking at energy efficiency or just power measurements in a network to help give deeper insights to help develop 6G.